So now we're going to take some time to look at radicals as well as rational exponents. When we're looking at radicals and more specifically when we're looking at exponential expressions, it's really important that we understand the base of the exponential expression compared to the coefficient. In the following example, 3 is our coefficient, x is our base, and 4 is the exponent. X is the only thing being raised to the power of 4 because it is the base. 3 does not get raised to the power of 4. So if we had, for example, x equals 2, when we evaluate this, we would have to raise 2 to the 4th power first, and then multiply it by 3. Now, conversely, over here, because of the grouping symbol, 3 to the x is now the base. 3x is our base, the whole thing being raised to the 4th power, which means that our coefficient is just the implied 1 that we can have in front as any coefficient. Now, when we're doing exponent operations, if we're adding or subtracting, we want to check that they have the same base and exponent. If they do, then all we have to do is add the coefficients together, as shown by this formula here. So here, we check to see our base and our exponents are the same. Our coefficients are 2 and 1, so we just add 2 and 1, and we keep the base and exponent the same. So we get 3x squared. Again, we check the base and the exponent are the same, so we're going to have x to the 3rd, but we can now subtract our coefficients, 5 minus 4, leaving us with 1x to the 3rd. Now here, we have x to the 3rd and y squared because the exponents are not the same. We cannot add or subtract. Here, our bases are different. Therefore, we cannot add or subtract. Now, multiplying, the only thing that has to be the same is the base. The base is the only part that needs to be the same. And so when we multiply or divide, we multiply the coefficients and then add or subtract the exponents based on whether it's multiplication or division. If we're multiplying expressions that have the same exponent, then what we can do instead is multiply the bases and leave the exponent alone. And that's given by these two formulas here. So let's take a look at some examples. Here, let's take a look at our bases. Our bases are the same. So what we can do is we can multiply the coefficients, and then we will add the exponents. 12x to the 3rd. Here we can divide because our bases are the same. So 10 divided by 2 times x, and then we subtract the exponents, 3 minus 2, giving us 2x. Here the exponents are the same, so we can multiply the bases and raise them to the common exponent. 12 squared equals 144. Here again, same exponent, so we'll have 6 over 2 to the 4th power. 3 to the 4th equals 81. Now here we don't have matching exponents or bases, but if we're clever, what we can do is rewrite 9 as 3 squared, and then raise it back up to that 6th power. And we're going to look at our product rule below, and our power rule says that we can multiply exponents when we have a power raised to an additional power. So we're left with 3x times 3 to the 12. Since our bases match, we can keep the base and add the exponents. Again, like I stated with our power rule, when we're raising an exponential to another exponent, we multiply the exponents. When the exponent is negative, we can remove the negative by writing the base as its reciprocal. And whenever we raise a non-zero base to 0, it always equals 1. So we can go ahead and solve a few more. Power rule states that we multiply the exponents. So 2 times 3 gives me x to the 6th. 2 doesn't have the exponent, it's a coefficient, so x we want to write as its reciprocal, 1 over x, and that will turn the exponent positive, and then we can simplify the fraction. Anything raised to the 0 power always equals 1, no matter how complex the equation is inside the grouping. Here we have our quotient rule, which means we subtract our exponents, but when we do, we end up with a -2, and so we then have to apply our reciprocal rule. Here we have 2 raised to the 2nd power, as well as 5 to the x times 2, so we get 4x to the 10th. 3 is a coefficient, it's not being raised to the 3rd power, so we have 3 times x to the 4 times 3, leaving us with 3x to the 12th. When we write reciprocals, functionally what it does is moves our variable and its exponent to the opposite side of the divisor line to make it positive. So here we can essentially just flip our fraction. We have y to the 4th over x to the 3rd. The x is our base, meaning it's the only thing being raised to the 0 power, so we have 3 times 1, -3 times 1, which just equals -3. Even if we have rational exponents, the same rules apply. If I have my quotient rule, I can divide my coefficients, and then I can subtract my exponents. So I'll have x to the 5 halves minus 1 half. So we have 4x to the 4 halves, which just simplifies to 4x squared. Again, we use our power rule, so we'll get 2 to the 3rd power times y to the 4/3 times 3. When we multiply 4/3 times 3, the 3's will reduce, leaving us with 8y to the 4th.